Welcome to ST102 Introduction to Probability Theory. I am Dr. Hemalika Abesundara from the Department of Statistics and Computer Science, University of Peradeniya. Let's start with the first chapter, Counting Techniques. These are the topics we will be discussing in this chapter. First one is the basic principle of counting, then the permutations, then the combinations, and we will be looking at several subcomponents of permutations and combinations, and also combination of all these three techniques. Let's look at an introduction first. There are problems in statistics and also in the real world where we want to find the total number of possible ways that a certain task can be performed. Say for example, if you want to find a password which contains 8 characters and it can have an uppercase letter, a lowercase letter, a numeric character and also a special character. If these are the conditions, how many different passwords that can you generate? Maybe there are some conditions imposed on the password, and depending on those conditions, what will be the total number of different passwords that you can generate? In order to answer these type of questions, we can use the basic principle of counting. Let's look at the first theorem. If an operation consists of 2 steps, of which the first can be done in n1 ways, and for each of these, the second can be done in n2 ways, then the whole operation can be done in n1 times n2 ways. Here, the operation stands for any procedure, a process, or a method of selection. Let's look at the justification for this theorem. We will define the outcome of the operation as an ordered pair xy and yi. Suppose the first steps xi result in probability n1 and the second step yi result in probability n2. Then the set of all possible outcomes will be n1 times n2 pairs. We can explain it further. Now suppose x1 contains the components x1, x2 up to xn1. Similarly, yi contains y1, y2 up to yn2. x1 can combine with either y1, y2, y3 or yn2. So the first line contains all possible pairs of x1 with each of y1, y2 up to yn2. If we go to the second one, x2 can pair with either y1, y2, y3 or all the way up to yn2. The second line shows you all possible pairs. If we continue it up to xn1, finally xn1 also can combine with either y1, y2, y3 or all the way up to yn2. So the last line shows the combinations of xn1 with all of yi. So which means if you combine all these pairs, at the end there will be xn1 times yn2, which means there are n1 times n2 number of possible pairs. Let's look at the first example. Suppose someone wants to go on a vacation either by bus or by train or by car to 5 selected cities, let's say Anuradhapura, Polonnaruwa, Katharagama, Galle or Bandarawela. Can you find the number of ways in which this can be done? If you choose to go by bus, you may go either Anuradhapura to Polonnaruwa to Katharagama to Badulla or Bandarawela. If you choose train, again you can choose either Anuradhapura, Polonnaruwa or one of the 5 cities. You can do the same with car, which means there are 3 number of ways to choose the transportation mode and there are 5 number of ways to choose the city. By applying theorem 1.1, the total number of possible ways will be 3 times 5, which is 15. Here's the second example. How many possible ways are there when we roll a pair of dice? One is red and the other one is green. If you look at the red dice, it has 6 possible outcomes. If you look at the green one, it also has 6 possible outcomes, which ends up with 6 times 6, 36 number of possible outcomes. We can extend the theorem if there are more than 2 steps in our operation. Theorem 1.2. If an operation consists of k steps, of which the first one can be done in n1 ways, for each of these, the second step can be done in n2 ways. For each of the first two, the third step can be done in n3 ways, and so forth. Then the whole operation can be done in n1 times, n2 times, n3 times, all the way up to nk times. Okay, here's the third example. A quality control inspector wishes to select a part from 4 different bins. The first bin contains 4 parts, the second contains 3 parts, the third one contains 5, and the last one containing 4 parts. If the inspector wants to choose a part from the first one, there are 4 possible ways. If he is going to choose a part from the second one, there are 3 possible ways. When he is going to choose the third one, there are 5 different components, and finally 4 different components from the last one. By multiplying all these possibilities, there will be 240 possible samples that the inspector can come up with. Next example. How many different ways can a student answer all the questions of a true-false test containing 20 questions? These questions contain only 2 answers. They will be either true or false, which means there are 2 ways to answer question 1, there are 2 ways to answer question 2, and likewise there are 2 ways to answer question number 20, which means the total number of possible answers will be 2 times 2 times 2 up to 20 times, so 2 to the power 20. So that will be the total number of possible answers that the student can come up with. Now let's look at the permutations. Here is the definition. Permutation is the different ways in which a group of objects can be ordered or arranged. When we say ordered, it has ranking, the first one, the second, the third, and so on. For example, how many different ways 24 members of a club can elect a president, vice president, a treasurer, and a secretary? How many different ways 10 songs can be played in a playlist? That means which song will be the first one, which song will be the second one, which will be the third, and so on. In these cases, you can see that one song cannot repeat. How many different ways 6 people can be seated around a round table? In order to answer these questions, you can use permutation. Here's the example. How many permutations are there of the letter A, B, and C? Since there are 3 letters, let's consider them as the first position, the second position, and the third position. Since we have 3 letters, the number of letters available to fill the first position, we have 3. Since we already selected 1 letter, now there are only 2 letters remaining to fill the second position. After we fill the first position and the second position, we have only 1 letter available to fill the third position. Then the total number of arrangements will be 3 times 2 times 1, which is 6. If you list all these possible arrangements, these are the 6 possible arrangements. By generalizing this example, n distinct objects can be arranged in n times, n-1 times, n-2 times, all the way up to 1 times. The notation will be n factorial. If you multiply a certain value n by reducing it one at a time all the way up to number 1, we define it as the factorial n. By definition, the factorial of 0 is 1. Here's the third theorem. The number of permutations of n distinct objects is n factorial. Let's look at another example. In how many different ways can the first 5 players of a cricket team can be sent to the ground? Well, the number of players available to go as the first, there are 5 players. For the second place, there are remaining 4 players. The third place, there are remaining 3 players. And likewise, you can fill 5 times 4 times 3 times 2 times 1 or 5 factorial, which is 120. So there are 120 different ways that these 5 players can be sent to the ground. Example 7. Find the number of permutations of 4 letters A, B, C and D. Using theorem 1.3, we can find the answer to be 4 factorial, which is 24. Can you try to list down all these 24 arrangements? Now in example 7, we consider selecting all 4 letters out of the 4. If you want to find the number of permutations of these 4 letters, if only 2 letters are selected out of them, then what will be the answer? Now we have to fill only 2 positions. So the number of ways to fill the position 1, there are 4 letters. The number of ways to fill the second position, there are remaining 3. Since we need to fill only 2 positions, there will be 4 times 3, which is 12 arrangements. I hope you can see the difference between selecting a few letters out of the all 4 and selecting all the letters out of the 4. Here are the 12 possible arrangements of selecting 2 letters out of 4. If we generalize this argument, we find that n distinct objects taken r at a time, where r is greater than 0, can be arranged in n times, n-1 times, n-2 times, n-r plus 1. We denote this product as n permutation r or npr. By definition, np0 is 1. Here's the theorem. The number of permutations of n distinct objects taken r at a time is npr, where we can calculate it using n factorial divided by n minus r factorial. Let's look at another example. In how many ways can a local chapter of the Applied Statistical Society schedule 3 speakers for 3 different meetings if they're all available on any of 5 possible dates? Okay, we know that number of days available equals 5, and the number of days to be selected out of that 5 available dates is 3, because we have 3 different speakers. Therefore, the total number of ways to select 3 days out of 5 will be 5 permutation 3. We can calculate that by 5 factorial divided by 5 minus 3 factorial. Hence, In the numerator, we have 5 factorial, and in the denominator, we have 2 factorial. If you expand the numerator, you will get 5 times 4 times 3 times 2 times 1. If you expand the denominator, you get 2 times 1. By cancelling out 2 times 1 at the top to the bottom, you will end up with 5 times 4 times 3, where the answer is 60. If you want to do this using a calculator, the NPR function is available in most of the standard calculators. Now by theorem 1.3, the number of ways to arrange 3 speakers will be 3 factorial, which is 6. Hence, by theorem 1.1, the number of ways the meeting can be scheduled will be 60 times 6, which is a total of 360 ways. So far, we have been assumed that n objects from which we select R objects are all distinct. What will happen if there are repeating objects? Let's look at another example. How many different permutations are there if the letters in the word book? In these 4 letters, we see that the letter O repeats twice. If we distinguish for a moment between the two O's by labeling them as O1 and O2, there are 4 factorial, which is 24 different permutations of the symbols B, O1, O2 and K. However, if we drop the subscripts, then BKO1O2 and BKO2O1, for example, both will yield the same formation BKOO. Hence, each pair of permutation with subscripts yield but one arrangement without subscripts, which means the total number of arrangements of the letter book will be 24 divided by 2, where the answer is 12. Example 1.11. In how many different ways can 3 copies of one novel and 1 copy of each of 4 other novels can be arranged on a shelf? If we consider all 7 novels are different, we will get 7 factorial, which means 5040 arrangements. But it is given that there are 3 copies of the same novel. Therefore, the total number of ways arranged will be divided by 3 factorial. Therefore, the final answer will be 7 factorial divided by 3 factorial, which will be 840. By generalizing the above argument, we get theorem 1.5. The number of permutations of n objects, of which n1 are of one kind, n2 are of a second kind, and all the way up to nk of an nth kind, and n1 plus n2 plus up to nk equals the total number n, is n factorial divided by n1 factorial times n2 factorial times up to nk factorial. Now let's try to apply this theorem. In how many ways can 2 paintings by A, 3 paintings by B, and 2 paintings by C be hung side by side on a museum wall if we do not distinguish between the paintings by the same artist? The answer will be 7 factorial divided by 2 factorial times 3 factorial times 2 factorial, because there are total number of 7 paintings. There are 2 repeating paintings by A, 3 paintings by B, and another 2 paintings by C. Therefore, the total number will be 210. Now let's look at circular permutations. Permutations that occur when objects are arranged in a circle are called circular permutations. Two circular permutations are not considered different if corresponding objects in the two arrangements have the same objects to their left and to their right. For example, if four persons are playing cards, we do not get different permutations if everyone moves to his or her right. Look at these four arrangements. In the first one, we see A at the top, and if you go clockwise, we have B, C, and D. Now in the second arrangement, we have moved A anti-clockwise, and the remaining three places are held as it is. In that second formation also we see B to the right of A and D to the left of A. If you move A another place anti-clockwise, still we have the same arrangement because B is to the left of A and D is to the right of A. And next, another place to the anti-clockwise for A, still you get the same arrangement. Therefore, A, B, C, D, B, C, D, A, C, D, A, B, and D, A, B, C. All these four formations are same. Therefore, we cannot consider them as four different circular arrangements. Now, how do we calculate the different circular permutations? If you want to find the different circular permutations, we have to fix one position and then rearrange the other remaining three. If we do that, there will be 4 minus 1, which means 3 factorial number of different arrangements. Therefore, if we have 4 persons sitting in a circular arrangement, there will be only 6 different circular permutations. Generalizing this argument, we get the next theorem. The number of permutations of n distinct objects arranged in a circle is n minus 1 factorial. Now let's look at the third counting technique, the combinations. Determining the number of ways in which R objects can be selected from n distinct objects without regard to the order is called combinations. We can select R different objects out of n without considering order, and those combinations can be calculated. Example 1.14. In how many distinct ways can a person gathering data for a market research organization select 3 of the 20 households living in a certain apartment complex? If we consider the order in which the households are selected, then we get the permutations, and the number of permutations will be 20 permutation 3, which yields 6,840 different ways. But each of the 3 households will then be counted 3 factorial or 6 times. But actually, the order doesn't matter here because what we need is to select just 3 households out of 20. If we disregard the order, the total number of ways to select 3 out of 20 will be 20 permutation 3 divided by 3 factorial. So the final answer will be only 1140. In general, there are R factorial permutations of the object in a subset of R objects. Since the order is considered NPR permutations of R objects, selected from a set of n distinct objects can be each subset R factorial time. The number of combinations or number of subsets of R objects that can be selected from a set of n distinct objects can be obtained by dividing NPR by R factorial. This result is denoted by NCR or n combination R. Theorem 1.7. The number of combinations of n distinct objects taken R at a time is NCR, which can be calculated as n factorial divided by R factorial times n minus R factorial. Let's try an example. In how many different ways can 6 tosses of a win yield 2 heads? So we have to select 2 out of 6, which will be 6 combination 2, which is 6 factorial divided by 2 factorial times 4 factorial, and the final answer will be 15. Let's look at this calculation. You see 2 factorial and 4 factorial at the denominator. If you compare these two values, 4 factorial is the largest number. If we expand our numerator up to that value, which means 6 times 5 times 4 factorial, rather than expanding 4 times 3 times 2 times 1, we can easily cancel out 4 factorial at the top to the 4 factorial at the bottom, which will make your calculation very easy. Then what we will get will be only 6 times 5 divided by 2 times 1, which was from 2 factorial. Therefore, the final answer will be 3 times 5, which is 15. Again, standard calculators will contain a button for combinations. Here's another example. How many different committees of 2 chemists and 1 physicist can be performed from the 4 chemists and 3 physicists on the faculty of a small college? Now there are 2 different groups. Let's consider the chemists first. The number of ways to select 2 chemists out of 4 will be 4 choose 2. The answer will be 4 factorial divided by 2 factorial times 2 factorial, where the answer is 6. Next, let's look at the second group, which is the physicists. The number of ways to select 1 physicist out of 3 will be 3 choose 1, where the answer is 3. By Theorem 1.1, the total number of ways to select the scientist will be 6 times 3, with the answer 18. Now let's look at set partition. A combination of R objects selected from a set of n distinct objects may be considered partition of n objects into 2 subsets containing respectively the R objects that are selected and the n minus R objects that are left. More general problem of partitioning a set of n distinct objects into k subsets, which requires that each of n objects must belong to one and only one of the subsets. The order of the subsets within a subset is of no importance. Consider 4 letters A, B, C, and D. If we want to partition this into 2 groups, each containing 2 letters, we can split A, B, C, D into A, B as the first subset and the remaining C, D as the next subset. Or we can split it as A and C in one subset and the remaining B and D in the next subset. Or we can split it as AD and then BC. So likewise, we can split the A, B, C, D, the 4 objects, into many different partitions. Theorem 1.8. The number of ways in which a set of n distinct objects can be partitioned into k subsets, with n1 objects in the first subset, n2 objects in the second subset, and nk objects in the kth subset, is n factorial divided by n1 factorial times n2 factorial times all the way up to nk factorial. Example 1.17. How many ways can a set of 4 objects are partitioned into 3 subsets containing respectively 2, 1 and 1 of the objects? So the answer will be 4 factorial divided by 2 factorial times 1 factorial times 1 factorial, where the answer is 12. Here is the next example. In how many ways can 7 businessmen attending a convention be assigned to 1 triple and 2 double hotel rooms? Since there are 7 total number of people, we have 7 factorial at the top and we group them as 3, 2 and 2. So we have 3 subsets. The first subset contains 3, the second subset contains 2, and the last subset contains the remaining 2. If you add 3, 2 and 2, you get the total 7. Now the calculation will yield 210 different ways. Example 119. A group of 100 students are planning to go on a field trip. There are 4 vehicles and the number of seats are as follows. We have a 52-seat bus, 26-seat minibus, 10-seat van and a 12-seat van. Now how do you split these 100 students into these 4 vehicles? Let's try to find how many different ways can we do this division. I will leave it for you to try. Let's look at the last example. A passcode of 4 digits is needed to access an account. Calculate the total number of different passcodes that can be made if all numbers 0 to 9 can be used and repetitions are allowed. Since there are 10 digits and all of them can repeat, the answer will be 10 times 10 times 10 times 10, because for the first position we have 10 digits to be selected. For the second position also there are 10 digits available. For the third also 10 and for the fourth also 10. By applying theorem 1.1, the answer will be 10,000. Second one. If all numbers 0 to 9 can be used but repetitions are not allowed. In that case, we have 10 digits to be selected for the first position. Since we cannot repeat, whatever the digit you chose for the first position cannot be used again. Hence, we have only 9 remaining digits for the second place. Then for the third place, you cannot use the 2 digits you have already used in the first and the second position. Therefore, we have only 8 digits to be selected for the third position. Similarly, for the fourth position, there will be only remaining 7 digits. If we multiply 10 times 9 times 8 times 7, you will end up with 5040. Number 3. If all numbers 0 to 9 can be used, but repetitions are not allowed, and the first digit cannot be 0. Now, you cannot use 0 in the first place, therefore, you have remaining 9 digits for the first position. When it comes to the second position, you have 0 and the remaining 8 digits, therefore, still you have 9 more digits to be used in the second position. Then there will be only 8 for the third and 7 for the fourth. So the total number of passcodes will be 4536. So likewise, you can end up with many different formations depending on the condition imposed on your formation. Here is a practice question. How many possible results are there for a draw of Mahajana Sampatha? Here is a sample of the Mahajana Sampatha draw ticket. It contains 6 digits and 1 letter in front of it. Can you find the total number of results that are possible in such a draw of Mahajana Sampatha?